stellar evolution theory yesterday. I will today do some more practical things. I will start talking about isochrones, or they are built, and then about simulations of star clusters and binaries. So first, isochrones, what they are. Evolutionary tracks are the locus of a given star of initial mass mi as a function of age that you already know from yesterday. Then that's what comes out from the stellar evolution codes. Isochrones are simply the locus of stars of a given age as a function of initial mass. So there's a one-to-one relation between grids of evolutionary tracks and grids of isochrones. So from the tracks we have properties like luminosity, effective temperature, surface chemical abundances as a function of age that we will convert as a function of initial mass for a given age. The problem is quite simple mathematically. The only technical problem, let's say, is that we cannot do this kind of interpolation that goes from evolutionary tracks to isochrones in a blind way. We need to do it in a somewhat clever way. Here is an example of what we have: evolutionary tracks in the plane age against initial mass. Evolutionary tracks run vertically. Isochrones run horizontally. We have here two sessions of tracks of two different masses. Let's suppose we want to build this isochron just interpolating between these two tracks. If you take these 2 points and just make a simple interpolation, it will not work. Why? Because these 2 points along two different tracks of different initial masses correspond to very different evolutionary phases, usually. For instance, in this high mass track, this point could be the end of the main sequence. In this lower mass track, it could be a point just at the beginning of the main sequence. If you interpolate between these 2 points, the result will be nonsense. We'll be interpolating between stars which have very different properties, very different luminosities, and effective temperatures. So what you do then is simply to work with interpolation between equivalent evolutionary points. So in these two tracks, you locate the beginning and the end of evolutionary phases and mark them like these 2 points. Let's say that's the end of the main sequence for these two tracks. That's, let's say, is the turnoff in the two tracks. We have two equivalent sessions of two different tracks, and you can safely interpolate between these two limiting points because they are pairs of equivalent evolutionary phases. What you do in between these points is also quite easy to figure out. You just locate a lot of pairs of equivalent evolutionary points along these sessions using parameters like the stellar evolutionary time, or maybe the central hydrogen composition or something like that. You make a lot of these pairs, and then later you want this isochron. You just look for these lines that cross this isochron and derive the properties via interpolation along these lines, exactly at those points. I just show that for 5 points, 5 pairs of equivalent evolutionary points. We can do that for hundreds or thousands of points along the tracks. In the end, we have isochrones, just by means of interpolations. Sorry. The graphical representation is essentially this one. We have planes of initial mass against age of the stars. We have a lot of horizontal lines, vertical lines, which are are the result of the cellular evolution code. And then we fill this plane with a lot of interpolations. In the end, we can derive detailed isochrones for any age across this plane. We do that for every evolutionary phase we are interested in. For instance, it could be simply the name of the evolutionary phase, as in this plot. Or in the right plot, we have something more interesting, which is the luminosity of the stars, from very small to very high. So something you can immediately see in this plot is that for an isochron, the section of the post-main sequence evolution that you cross is very short, very narrow in the interval of initial masses. That's the reason why when you look at an isochron and compare to a track, you have something very similar for any post-main sequence phase of evolution. Just because the range of initial mass of a typical isochron is very narrow. Of course, this is not a general rule. We have also parts of this plane in which we have something more strange going on, is that we have an isochron in this case that just crosses 3 times the terminal pulse AGB, and the result will be that we'll have an excess of AGB stars in that particular isochron. That's just an example that it's at first, as a first approximation, correct to say that the post-main sequence part of an isochron is corresponding to an evolutionary track, but is not strictly correct. Sorry? In this plot, that's luminosity. Scale between logarithm of luminosity between 0 and 4. Yes. So, of course, the groups that are computing evolutionary tracks do this job of interpolating carefully between equivalent evolutionary points. They provide both the evolutionary tracks and the interpolated isochrons. So you don't need to do that again. As you can see here, we have just an example from the parsec database. We have a lot of tracks which are quite close in mass, so that they allow us to make very accurate interpolations and derive isochrons from very young to very old ages. We have also a few web servers in which you can go there and look for an isochron. That's an example from the parsec isochrons. I work with that, so that's my preferred example. You go there, you just select the evolutionary tracks you want, the interval of ages, the photometric system, click, and then you have, as a result, tables of isochrons for a given age, or for many ages, or for many mentalists, with a lot of properties of the stars along the isochrons, like initial mass, actual mass, considering mass loss, luminosity, effective temperature, gravity, the magnitudes, both the bolometric and the JHK in this case, and that's the integral of the IMF up to that initial mass. And this last column is the evolutionary stage. So all that is available from several groups, actually. Let's give a look of how isochrons are converted in these basic physical properties into magnitudes. In this case, absolute magnitudes. That's all is described in this paper, 2002. There are some other papers in the literature, like by Bessel, which not just a single paper, but a few ones which tell exactly the same thing. That's just a kind of summary of all steps you do to convert the luminosity and effective temperature of star into absolute magnitudes. For doing that, what you need are spectral energy distributions of stars as a function of effective temperature, gravity, and chemical composition. You need a set of filter curves like these ones from Sloan. They tell us which wavelengths are transparent to radiation. So which part of the spectrum of the star will be collected by the detector, let's say. And then you need a set of 0 points, which is just what will give the absolute reference to the magnitude scale. Spectral energy distributions look like that. That's F lambda in units of ergs by square centimeter by second by angstrom. You have from very hot stars like Vega to normal stars like the Sun to cool stars like M5 giant in this case. That's F lambda against lambda. So those are the ingredients. The formalism is described here. That's the equation for the flux of the star as it arrives on the Earth. It's given by a term which is the extinction, interstellar extinction, 10 at minus 0.4 times the extinction. That's the A lambda in this case is the extinction in magnitudes. Then we have a dilution factor, which is the ratio between the radius of the star, because the radiation left the surface of the star, and the distance from the star to us. And you have this term to the square of to the power of 2 times F lambda, which is the radiation as it leaves the surface of the star. Then what else we need is the definition of the apparent magnitude of the star in one filter. That's given by this equation, which is minus 2.5 times the log of a ratio between two flux integrated on a given filter. You do not have simply the apparent flux as it arrives on Earth. You have it multiplied by lambda, because that's not an integration of the energy of the photons, because F lambda is in energy units. You need an integration that takes into account the number of photons that arrive, because nowadays we are using, almost all people are using modern systems which count photons and not the energy of photons, like CCDs and infrared arrays. So that's the integral which will take into account the numbers of photons arriving at my detector compared to the numbers of photons that would arrive from a reference spectrum, F lambda 0, plus a magnitude which is just set in the absolute scale of the photometric system. So what we want to do is to derive the absolute magnitudes for all stars in our isochrones. But in the database of synthetic spectral stars, F lambda, we have that as a function of effective temperature, gravity, and metallicity, usually. If you simply write the equation for the absolute magnitude of star, we just put our star at a distance of 10 parsec. That's the definition of the absolute magnitude of the star. The magnitude of a star that a star has at a distance of 10 parsec. We simply put that in the previous equations and get this formula, which is simply derived by the previous one. But as you see here, we have still the radius of the star here. We should get rid of that because the radius is not in the library of spectra we have. You get rid of this radius just working with bolometric corrections. The definition of bolometric corrections is here. It's just the difference between the bolometric magnitude of the star and the absolute magnitude in a given filter. Questions? No? So, the bolometric magnitude of the star is given by this equation. It's just, by definition, this minus 2.5 logarithm of luminosity of the star with respect to the sun, corrected by the bolometric magnitude of the sun, which is by definition something like 4.7. You can insert here the luminosity of the star, which is 4p times the square of the radius times the bolometric magnitude of the star. If you substitute this equation in the previous one, you'll get finally the equation for the bolometric correction for a given filter for a given star at a distance of 10 parsecs. It looks like this. It's very easy to see that we have just a series of constants here times the bolometric flux of the star. And this is just the integral of the spectrum of the star, synthetic spectrum of the star, convolved with the filter and extincted by a given A lambda. So, as you see, this equation does not depend on the, it depends only on the shape of the spectra F lambda you have, on the extinction curve, on the shape of the filter. So, this is all the bolometric corrections look as a function of effective temperature. You have always something like that, a curve which has a maximum depending on the effective temperature and on the filter, and sharply falls towards very high and very low temperature. That simply, this is simply the maximum caused by the fact that you are sampling the maximum of the emission of the star. Of course, if you have very cool stars, you'll be sampling more this part, so this part of the curve will be higher. If you have very hot stars, you'll be sampling more that part of the curve. Anyway, you can take a library of stellar spectra from the literature and make these tables of bolometric corrections that will allow us later to interpolate inside these tables and then compute the bolometric correction for every star you have in the isochron using the right temperature, metallicity, and gravity of the star. Simply using that equation to get the absolute magnitude of the star. So that's what's done usually. For every isochron we have, you can convert to many photometric systems just applying this procedure. What about 0 points? They can be of a few types. Especially important are the Vega-Mag systems. They are based on an assumption that the star Vega has a magnitudes in all filters which are very close to 0. Not exactly 0, they can be something like 0.03 magnitudes. But anyway, the usual assumption is that all colors of the star Vega should be 0 in that system. They were very used in the past just because they are the base of the Johnson-Cousins glass system, which has been very popular for decades. Now they continue to be used also because the HST observations are usually, at least for stars, are usually expressed in Vega-Mags. And also, TUMAS adopted the Vega-Mag system, surprisingly, because it's a near-infrared system, but they decided that Vega should have 2 mass colors of 0. And then that's a reason why almost all infrared systems now just adopt Vega-Mag 0 points. Of course, to reproduce the Vega-Mag system, we need a spectrum for Vega. We have a few ones available in the literature. Like the ones by Ayes and then by Bolin. There are also a few syntactic spectra for Vega, like those by Castelli and Kurux. They find that Vega has a temperature close to 10,000 Kelvin, a gravity of about 4, a metallicity of minus 0.5. So all parameters of Vega are almost accurately known. We have all the spectra for Vega that we need to make this kind of synthetic photometry. The only detail maybe is that we have to take the observational spectra of Vega and scale by this geometric dilution factor, which is the ratio of the radius of Vega to the distance of Vega to the Earth. But this scaling, this dilution factor is quite well known for this star because we know its distance. We know also, especially know the diameter of Vega. It has been measured. So, second kind of photometric system, which is particularly important, are the AB mag ones, or AB magnitudes. They are based on assumption that spectra of constant flux density with this value of flux as magnitude equal to 0 in all passbands. They derive from a paper by Oak, or an idea by Oak in 1964, which would define the monochromatic AB magnitudes to convert observed spectra to a magnitude scale using this definition, which corresponds quite well to this one. The only difference is that this was a definition for 1 lambda. If you want to use these systems, we have to make exactly this same kind of integral we have done before, integrating the flux given here, convolved with the filter transmission curve using this formula. But anyway, that's exactly similar to what I have shown before. The equation does not change. What changes is just the reference spectrum and the reference magnitudes for these AB mag systems. They are now very common just because they have been adopted by Sloan Digital Sky Survey. And a few major surveys are still adopting them, not only for the galaxies, but also for the stars, like Pan-STARRS and DES, and also the surveys by the CFHT. So, most modern systems are either Vega mags or AB mags. We have also some historical systems, like the Vilnius and Tuangan, which do not use anything like Vega or AB. They are based on the magnitudes of a few standards, like these 4 metal pulsar subdars, which were very well calibrated by Oak and Gunn in the past, and then they were used as a reference to the magnitudes of many photometric systems. But now, of course, they have been replaced by other definitions of 0 points. What about the libraries of F lambda that we need to make this conversion or these tables of bolometric corrections? We have many available. That's just an example of what I use as a function of effective temperature between very cool and very hot stars, and log G for dwarfs and giants. In green, I hope you can see well, that's the whole region covered by the Kuruk spectra. Moreover, Kuruk spectra covers 7 or 8 metallicities from slightly super solar to minus 3.5 or something like that. So that's a very good coverage of the region of log G, log TF that we have to cover. But we have also some alternatives now like Marx and Phoenix. And, well, I didn't show them here, but they are starting to cover a region of the log G effective temperature plane as large or about half as large as the Kuruk's one. And then we have special libraries like the one by Aringer et al. 2008, which are made for carbon stars. So special stars which are in this region of the HR diagram, but are not covered by these codes, just because they correspond to a very particular chemical composition of the star. What else? We have also this region of the diagram. These are models. Essentially, they are Phoenix models for very low mass stars by the group of Allard. We have some few libraries for M giants. Anyway, I will not enter in details here. The basic message is that all the interesting region of this plane is basically covered. It can be improved. It will be improved, but the situation is quite good now. What about extinction coefficients that we need also to make the syntactic photometry of the stars? Everything you need to derive then are a good extinction curve as a function of wavelength. And we have that. That's the classical Cardelli et al. 1989, corrected by O'Donnell in the UV. And we need a method to derive the extinction coefficients. That's essentially this one. That's the extinction in a given passband with respect to the extinction in the V band. That's given only by the difference between the bolometric corrections in these two passbands. No, not in these two passbands, but between the no extinction case and the case with positive extinction. They are divided by AV, which is the total extinction. So a very simple way to derive the extinction curve is just adopt the previous formulas, which have a term for the extinction curve, and then make these differences between bolometric corrections. What you get are things like this. That's A lambda divided by AV, sorry for the low quality, against the effective temperature, or the logarithm of that, for several passbands going from blue ones to red ones, as I said, as a function of effective temperature, from very hot to very cool stars. As you see, the A lambda over AV are not constant, not strictly constant. They are generally quite constant for hot stars, but for cool stars, they fall. They become smaller. This effect is called Orb's effect, or heterochromatic extinction. It's caused simply by the fact that with different spectra, you are weighting different parts of the extinction curve in a different way. Also, we can show quite easily that extinction coefficient divided by AV does not only depend on temperature, but also depends on how strong is the extinction. Please?
These coefficients are derived from an extinction law?
Yes. Yeah, in this case, for R equals 3.1. You can make the same for whatever R using the Cardelli extinction curve. So also in this case, we have a small change of these coefficients with how strong is the extinction, the total extinction. Anyway, the effect is small, but if you want, you can compute it and take it into consideration. In most of the cases, you'll be in this flat region of the curves and will not do any correction. But if you're looking, for instance, to the bulge using an optical filter, maybe it's better to consider this kind of effect. And also to consider the fact that the RV is not exactly 3.1, it can be larger than that. Anyway, we have all ingredients to take that into account. So, that was regarding how isochrones are converted in different photometric systems. We have another problem now, is how to populate an isochron. For that, we need the initial mass function, which is giving me exactly what's the probability of having stars in every being of the initial mass range. As everybody know, we have the saltpeter-like IMFs, which give the IMF as a function of just as a simple power law of the initial mass multiplied by a constant. Within a given interval, of course, we have to impose a cutoff to this saltpeter IMF. Otherwise, you get an integral of the IMF, which is infinite. Anyway, we impose a lower limit to the stars, like 0.1 or 0.2 solar masses, and we have something that can be used to populate the isochrones or the initial mass scale of the isochrones with stars. For whatever IMF you have, you also need to consider what kind of normalization constant we want to use for that IMF. You can have two cases, which I think are quite useful. You can normalize that so that the integral of the IMF over the entire mass interval is equal to 1 star. In the case of the saltpeter IMF, this condition just implies that you have this kind of constant, normalization constant. But another possible choice, which is quite useful, as I will show you tomorrow, is a normalization in which I impose that the integral of the mass of all stars in the population I have is equal to 1 solar mass. So that's a simple, if I normalize in that way, I can have an IMF with which I can easily simulate later 10 to the 4, 10 to the 5 solar masses of stars. That's what I need to have actually for modeling galaxies. So how do you populate the IMF? We have a few papers that show you how to do that, like Girardi and Santos de Frogel. You can also look at the numerical research books. There's a chapter about Monte Carlo methods, which tells everything, even in the first page, about how you can generate random stars following a given probability distribution function. In this case, we want to generate random stars following the IMF. It's useless to explain that how that works mathematically, because there's a very easy way to understand that graphically using this kind of plot. If I have a flat probability distribution function, like in this case, I know it's very easy to simulate objects that fall in this range. I just convert this flat function into a cumulative probability distribution like this one. That's a function that goes from 0 to 1 linearly, exactly linearly. And if I generate any random number in this interval, I will have I will easily locate my position in this plot and take the property that I want. In this case, it's so straightforward. I just generate a random number between 0 and 1, and that's the number I want. In the case of IMF, I have a probability distribution, which is something like that. Generally, it's for the saltpeter IMF, it's a power law, decreasing. I can easily, with any numerical code, convert this function into a cumulative probability distribution as a function of the initial mass, like this one. This function goes from 0 to 1. I generate random numbers along this x between 0 and 1. I locate random number here and easily read here what's the mass I have generated in this plot. Is that clear? It's obvious from the IMF that I have a larger probability of having low mass stars here. And using this procedure, I generate a random number here. Go here, read the number, the mass of the star. I have that it's a low mass star. It's exactly what I wanted to have. Okay?
You repeat the process until the desired number of stars.
Yes, you do. Yeah.
1 billion stars.
If you have 1 billion, you do it 1 billion times.
Yeah.
Yeah. Of course, you have some other details. What to do if the star is a binary, but that's later. Or what to do if the star is a dead star. It happens very often because if you generate a massive star and you have an isochrone of age of 10 to the 8th years, it's out of the isochrone. So you simply not find it here. It's out.
Just to be clear, you don't do this for building isochrone.
No, that's after I have the isochrones. Yeah, that's for generating initial mass that I locate inside the isochrone, because I have the MI all along the isochrone. So you can do that easily, and what you get are plots like that. That's for isochrones of increasing age. The logarithm of the age is here, going from young to old. You generate random initial masses and locate it inside the isochrone and put a dot there. And what you do, in the end, you are populating the isochrone where the stars should be, exactly in the most long-lived phases or on the main sequence. It's quite easy and it works. But then we have the complications. One obvious is about binaries. Binaries are not given by the IMF. The IMF is for single stars, by definition. For binaries, you need some other prescription. And we have different types of binaries. We have the apparent ones, which are caused by just the casual superposition of two stars randomly in your field of view. That's similar to crowding. Just two stars fall in the same place of the image. So the photometry you get is for the total flux of the two stars, not of one. That's very easy to simulate. You just take stars, pairs of stars at random, and sum their fluxes. A little bit more interesting are the detached binaries, which are stars which are physically associated, but too far away so that the evolution of both stars is independent. They will never interfere with the evolution of each other. So the detached binaries will appear in numbers which will be proportional to the numbers of stars and not to the density of stars in the image I have. And also, the mass ratio will not be random. The properties of the stars will not be random because some kinds of physical binaries are much more likely than others. So we need a prescription for that. We can find a few empirical ones, but I think there is not something like an IMF or mass or universal mass ratio distribution for detached binaries. That's something that we can adopt a few reasonable prescriptions, but they are not very well justified by observations because it's something that is just starting. Probably after Gaia, you'll have a lot of very good prescriptions for this distributions of mass ratios. Anyway, in both cases, we have a few effects on the color menu diagrams of the stars. The most evident one is this one. You can see it in a paper by Early and Taut. This is the main sequence of single stars. When you add stars, along the main sequence, of course, you'll have that you'll form a sequence of binaries which is above the main sequence. If you have two equal stars, they will be located 0.7 magnitudes above the main sequence. 0.7 is just the minus 2.5 times the logarithm of 2. So that's the limit for the detached binaries in column random diagram. And also we have some star spread. That's a simulation, actually. You have a kind of accumulation here at the border of this sequence. But you have all region in between these two limits filled with detached binaries. The closer you get to the real main sequence, the larger is the mass ratio between the stars. And actually, this is quite easily observed in almost all star clusters that we have in the literature. Please. So we have good numbers for star clusters in magnetic clouds because it's easy to make, well, not easy, but with HST we can do quite good photometry and count quite accurately these stars along a sequence which is parallel to the main sequence. The fraction that turns out is 0.3, 30%. About, of course, it changes from cluster to cluster. It is smaller in global clusters, which are very dense. But okay, 30% is a typical number.
But that's just, I guess, if you're talking about HST photometry, it's just the eclipsing binaries.
No. For detached binaries. For non-eclipsing binaries in general. They are in the same position of the image.
Basically, have the resolution which is good enough to separate the pair if it is detached.
But not in distance clusters. If you are looking at star clusters inside the galaxy, we have a good resolution, may separate. But if you are looking at clusters at more than 20 kiloparsecs, you cannot separate the binaries.
Well, we can talk about this later because I don't think that we are understanding each other.
Okay. Okay, later. As you prefer. Sorry. Okay, that's about binaries that do not interact. They never change the evolution of each other. Another aspect I should have mentioned is that in the evolved part of the color magnetic diagram, we have a very modest dispersion of the photometry of the stars, just because the probability of having a binary made of two giants is very small compared to the probability of having a binary between two main sequence stars, just because of that. So we have just a modest dispersion in the color magnetic diagrams in all the evolved part of it. What about interacting binaries? Then, okay, these are those stars that will, at some point of their evolution, one star will evolve and fill the Roche lobe and transfer mass to the secondary. The evolution can follow many different ways, and it's a kind of crazy field of crazy part of stellar evolution theory in which we have many kinds of different evolutionary paths being followed, and a wide range of possible results too. We have the production of blue stragglers, X-ray binaries, symbiotic stars, nova, supernova type of main, all kind of exotic stars. Not all, but many of them are caused by the interacting binaries. Fortunately, they are not that important in low-density environments like the disk of the Milky Way, let's say. But they are especially important in dense environments like the core of globular clusters, things like that. And also for massive stars. Anyway, we have some good, well, I would say excellent models for the evolution of binaries provided by this paper by Early et al. Their group designed a binary stellar evolution code, which is a kind of synthetic code that quickly computes the likely evolution of a binary, giving a series of parameters, especially the mass of the components, separation, the eccentricity of the orbits. It cannot be said to be accurate because the field is so complicated and we know very little about the initial conditions of these binaries. Anyway, it's quite a good start. As shown by the group of Early, they can use that code to predict things like the populations of blue stragglers in open clusters. That's the observed color band diagram of M67 with an age of 40 gig a year. You can see here the likely blue stragglers. And this is a simulation of the same cluster, adopting, of course, a distribution of mass ratios, separations, etc. for the binaries. And they get a population of blue stragglers. So it's becoming possible now to simulate these interacting binaries using this kind of code. So I think that's all for today. I hope you have learned how it works to produce simulation of star clusters. And I would even suggest some homework for you. Since this is a school, if you want to make an exercise, you can try, for instance, just read an isochron from any database you have and try to generate yourself a synthetic HR diagram for, let's say, 1,000 stars following saltpeter IMF. If you can do that, you can simulate any cluster of any age and any metallicity. And if you do that, tomorrow you'll learn how to make a galaxy, just expanding this process. Also, the problem is so easy that you can do it directly with a plotting code like SuperMongo. Actually, I do it with SuperMongo all the time. You just need 10 lines of code, and you can do that in 15 minutes. If you do that, if you don't go to the swimming pool, let's say. Okay.